Hi everyone, welcome to the module 3 of data structures and algorithms. So far we have covered how to analyze our programs using three different approaches as well as various linear ordered data structures that include lists, stacks and queues. Today we'll start with our first non-linear data structure, which is trees. Our agenda for today includes we'll be covering what is the terminology that's used for an abstract data type of a tree. Also, we'll discuss what are the different types of trees, and we'll go into a specific type of tree that is commonly used, which is called binary search trees. We'll discuss its properties, how we can insert elements, how we can delete elements, and what are traversals as well as what is searching in the context of trees. So let's get started. So trees is basically a data structure that is rooted, directed, and acyclic in nature. If you're confused by any of those words, don't worry, I'm going to explain you each of them in just a second. Basically, a tree has few properties, and to be precise, just three of them. The first one, it has just one root, which is if we are drawing a tree in the context of computer science, there's just one root, which is kind of the head element. And out of this, there might be multiple nodes. The second property is each node has at most one parent, which means, like, if this is node X, it can have only one parent that's called Y. It cannot be something like this, which is it cannot have two different parents. Like in the context of this, we are going to define what parents and children are, but for the sake of simplicity, you can consider parent giving rise to children here. So basically, X is the child of Y and Z in this case, but this is not a valid tree because our tree's definition is that each node has just one parent. And finally, the third property is that there are no cycles in the tree, which is this the tree cannot have something like this, which is this is now a cycle. So you cannot have any cycles in a tree. Also, I want to remind you that tree is a specific example of graphs, which we are going to cover in the future. Uh, but basically, tree is like a subset of graph. If a tree has cycles, we can call it a graph. And we are going to discuss that more in week 6. So let's discuss, like here in the example, you can see a tree. Now, one important point to note is it can have any number of children because it's this tree right now that's shown to you here satisfies all the three properties. It has one root element, which is this 25. Each node has one parent, which means the 2 has one parent, which is 25. 15 has one parent, which is 25. 51 has one parent, which is 25. And 5 has one parent, which is 2. 11 has one parent, which is 2. And 65 has one parent, which is 51. This property, which is each node has one parent, is excluded for the root element because the root will never have any parents. And you can see in this tree that there are no particular cycles, which is like none of these are joined, so there's no cycles. So the use cases that you commonly see around yourself as well as in computer science is trees are frequently used to model different scenarios, which is in case like you might have already heard about the family tree, which is like let's say if you have some surname like Smith, it has some other name like John, Ralph, Jane, and so on. So like this is an example of a family tree where uh, let's call these like some names where Ralph is kind of the parent of Jean and Smith is the parent of Ralph and so on. Another use case of this trees is something called decision trees. So if you study like machine learning, uh, in the future you will encounter something called decision trees, which is let's say if you are making a flow chart. An example is checking whether a number is an integer or not. I'm like simplifying this with, but something like if you have a number n and you want to check if this is even or odd, you're going to basically do something like n mod 2 is equal to 0. If this is true, your system takes this route, while if this is false, your system takes in this route. So you can make like very complex scenario based on this, which is true and false. And this is another example of where trees are frequently used. Another example is file system. So a Linux file system is typically represented by a tree. Even your hard disk, like a hard drive, has a file system in Windows or Mac that also is represented by some type of tree, which is not exactly binary tree, but we are going to discuss like B plus trees next week. File systems such as you have this root node, which is the central node of all, or the parent node of all the other nodes. And let's say if this root node contains different subfolders, which include, uh, let's say I have some desktop, I have documents, I have my C drive, and so on. And then within each of these folders, there might be further folders or files. Another example is expression trees. So last week when we covered stacks, we discussed like you can evaluate expressions like 2 plus 4 divided by 3. These can also be represented in the form of trees. I'll give you a concrete example here, which is, let's say if we represent this by a tree, this syntax, this expression can be represented by in the form of tree. And the last one is search trees, which is like, let's say if you have an entire dictionary, we can represent this by like another some type of tree, which is like, let's say if the parent node is an empty string, and then you have the first node has a, b, and it has like 26 different nodes. So you can represent, or all the words that start with A fall under this node, all the words that start under B under this node, and so on. So again, after A, it could be like AA. And then each of the levels, which is each of these children of a particular parent, represent first initials of a particular word. So let's discuss a few elements of the terminology of trees, like what are the different constituents of the trees, as well as what terminology we use. And we are going to discuss that in the next video.